All right, welcome back. Today we're going to continue the discussion of probability, general rules of probability. We're going to talk about the multiplication rule. All right, so reminder from the last video, we talked about the addition rule. There were two addition rules. When two events are disjoint, we can just simply add their probabilities. The probability of one event or the other event, E or F, is the probability of the first plus the probability of the second, P of E plus P of F. And the example, one example that we might use for that is the probability of selecting an ace from a deck of cards or selecting a king. Since those events cannot occur at the same time, is simply the probability of selecting an ace plus the probability of selecting a king. How many aces are in the deck of cards? There's 4 aces out of 52. How many kings? There's 4 more kings for a total of 8 out of 52. So we can just add those together. When two events are not disjoint, we have to subtract off the probability that they can occur simultaneously. So the example, or an example, would be if we changed the king to a heart, right? An ace or a heart. Well, the ace of hearts is one of the cards. So if we say 4 out of 52 for the aces and 13 out of 52 for the hearts, we have to take away that one ace of hearts. So we can't say 17 out of 52, we have to say 16 out of 52, which can be turned into a fraction, a decimal, or a percent. All right, but what if we want to find the probability that two separate events occur one after the other? So we're really talking about two individual events. Okay? Well, we use what's called the multiplication rule. All right, so before we can use the multiplication rule, just like with the addition rule, we have to consider if one event occurring will actually affect the probability of the other event happening. Because if it does, then it's going to change the outcome. So, for the events to be independent means that the first outcome, in other words, the first thing that happens, does not affect the probability of the second thing happening. So, for example, we draw a card and then we replace it. We replace that card back in the deck and then we reshuffle before the second drawing is made. These will always be independent because you're replacing the card, there's still going to be 52 cards left in the deck. Okay? Similar outcomes are allowed to repeat themselves. Okay? So, for example, if you use the digit 1 in a pin number, usually you can repeat that digit. Okay? Obviously, selecting a pin of 1111 is probably not the best idea in the world because it's easily guessed, but it is possible in some cases. Okay? So in that case, selecting a 1 for the first digit, because it's replaceable, is independent from selecting a 1, which is independent from selecting a 2 for the second digit, which is independent of selecting a 4 for the third digit. Okay, dependent events, as you can imagine, are not independent. So the probability of the first outcome affects the probability of the second one. Now, what if we draw a card and then we don't replace it? How many cards are left in the deck? Remember, there originally were 52. So let's say the probability of selecting an ace, 4 out of 52. Okay? That's the probability of selecting an ace. Now, what's the probability of selecting another ace? Let's make this A1 and A2, right? So what's the probability of selecting another ace if I know that I already took one out? In other words, I already took out an ace on the first selection, is the probability of getting an ace on the second selection the same, or is it different than the first selection? Well, there are only 3 aces left in the deck, and there's only 51 cards left in the deck. So, of course, this fraction is not the same. And just to be clear, if I do 4, let's clear this out. 4 divided by 52 gives me 7.7%, but if I do 3 out of 51, now we're at 5.9%. So way different, okay? So what that tells us is that A2 and A1 are dependent because the selecting an ace on the first selection does affect selecting an ace on the second. People who play blackjack and poker know this information because they utilize this information to help them place their bets. Okay, there's fewer outcomes possible now in the sample space, which indicates there's going to be a different probability for the second event, just like we said. Now, what if a number is not allowed to repeat itself? So sometimes in certain passwords or PIN numbers, you cannot repeat the same number. So here, selecting a 1, right? You have 10 selections for maybe 10 selections for the first digit. Well, the second digit is not going to have the same number of selections now. You can't use a 1, right? So the probability of selecting a 2 increases after I've used the 1. So if we have 10 digits to choose from, then selecting a 1 gives us a probability of 1/10. But selecting a 2 after selecting 1 as our first digit, the probability of selecting a 2 increases. And by that I mean there's one of the digits is a 2, but now there's only 9 digits to choose from, and 1/9 is larger than 1/10. So that's what we're talking about here. Okay, so the multiplication rule for independent events says that the probability of the first event and the second event is the product. This is a multiplication sign, okay? Product of the probabilities. Now, this is not to be confused with P of E and F, meaning the probability of E and F occurring at the same time. Okay, that's not the same thing. This example is used when we have a single selection or a single trial. Okay, so in a single selection, notice we have the exact same notation here, but it means something different. Here it means that they're occurring at the same time. So like the case of the ace and the heart, right? The ace of hearts. That is the P of the probability of both of those occurring at the same time. This is saying we're getting E on the first trial and F on the second trial. Okay, so we just multiply the probabilities if they're independent. All right, so again, 2 independent events, meaning that when the first event occurs, it does not affect the probability of the other event occurring. So think about choosing 2 cards, one after the other. After the first card, you replace it back in the deck and you reshuffle. So supposedly it's random. Okay. So what is the probability of choosing a king on the first selection and a 10 for the second selection? Okay, I'm using subscripts here for first and second selection. You can use whatever notation you want. So the question is, are these events independent? So independent, question mark, yes or no? The answer is yes, because we are replacing the king in the deck and reshuffling. Okay, so this will be the probability of a king, 4 out of 52, times the probability of a 10, 4 out of 52, which will be 16 out of whatever 52 squared is. So first thing I'm going to do is illustrate what the fraction will look like, 2704. Okay, so 16 out of 2704. Okay, so again, I can calculate that as a decimal. So I can say 16 divided by, now instead of retyping the 2704, you can use this ANS function, which is the second function of the additive inverse key. So if I click the second button and that one, okay, what that does is it gives me the decimal probability there, 0.006 approximately. Okay, so it's approximately 0.6%, 0.006, excuse me, so 0.6%. So a very low probability that you would select your first card being a king and your second card being a 10, but that is the probability. Now, the other thing I wanted to mention in the calculator was if you wanted to view the decimal as a fraction again, a simplified, I should say, a simplified fraction, remember that we can click math and then fraction, and it'll turn it back into a fraction. So 1 out of 169 is the simplified probability. So 1 out of 169, which tells me that 2704 is divisible by 16. Okay. So the probability is about 0.6%. Oops. I keep doing that. I like the little eraser, though. It works good. All right. So here we go. 4 out of 52 times 4 out of 52 reduces to 1 out of 169, just like I mentioned, 0.6%. Now, here's a table of blood types, type O, type A, type B, type AB. Now, this gives you some information just by looking at the table. So here's a question. Which type is most prevalent? Well, of course, it would be the one with the highest probability, right? The highest percentage. By the way, probability and percentage mean the same thing, right? The percentage of the population, or also proportion. They all basically mean the same thing. So the probability of people with type O, the percentage of people with type O, the proportion of people with type O is 44%. Okay. So those basically are interchangeable. All right, 2 people are selected simultaneously, so we're picking 2 people, and at random from all people in the United States. What is the probability that both of them have type O? So the probability that the first person has type O and the second person has type O. Now, do we expect this to be independent? In other words, is the selection of the first person with type O is going to affect or not affect the probability of the second person? Now, this is in the entire country. So I grant you that if you took, the entire population, say about 300 million, and you selected how many of those people have type O, which would be about 44%, right? So 44% of 300,000,000 is 132 million, okay? And then that's the probability that the first person has type O. But the population size is so large, we don't use that, right? We just say that the probability is 0.44. And the probability that the second person has type O is 0.44. So when the sample size is large enough, we don't worry about removing one from the population who has type O, removing one from the general population. So when the number is somewhere, I believe, 100 or larger, Okay, when it's a large enough population, we don't worry about that, so we assume that they are independent. The assumption is that they are independent. Therefore, I would just multiply the two probabilities. 0.44 times 0.44. Okay. So 0.44 squared is 0.1936, which is 19.36%. There it is. %19.36%. Okay, so dependent events. So once again, the independent rule, let's go back to that, is that you multiply their probabilities. Right? You multiply their probabilities and that's it. Okay. For dependent events, it's a slightly different. You still do some multiplication, but we use what we call the probability of the second event given the first event. So F bar E means probability of that, means the probability of F, comma, given that E already happened or occurred. So we have to take into account that the first event already occurred, and then we can look at the probability of the second one. So what about two face cards in a row? Now, face cards are jacks, queens, and kings, right? Those are the face cards. So there's 4 of these, there's 4 of these, and there's 4 of these, for a total of 12 face cards in the deck, okay? And we're going to do it without replacement. So we can ask the question, are these events independent? Are they independent? No, because they're being selected without replacement, which means that you select a face card, maybe a jack, you put it in your pocket, okay? Which means that selecting another face card, either another jack or a queen or a king, will affect that probability, okay? So the probability of selecting a face card in the first trial is 12 out of 52. But the probability of selecting a face card in the second trial, given that you already selected one, you have to take into account that you already picked one out. So 11 are left and 51 cards are left. Okay. So again, 12 out of 52 times 11 out of 51, 12 out of 52 times 11 out of 51 will be, parentheses, 12 divided by 52, close parentheses. And you don't even have to hit the time symbol. It knows that when you have another open paren, you're going to multiply. 11 divided by 51. Now, when I click the enter button, it'll give me a decimal. So that's fine, but if we want to see it as a fraction, we do the fraction key. So 11 out of 221. That's the simplified, okay? Okay, so 5%. So as a percentage, once again, you can just 11 out of 221. I can turn it back into a decimal like that. There's your 5%. So 4.98%, so about 5%. So about a 5% probability that you'll get 2 face cards in a row. You can do the same, you can use the same idea to calculate the probabilities of all kinds of things here. So here it says after the first one was drawn, there are only 11 more possible successes out of 51. So that's where the 11 out of 51 came from. So things to remember. Disjoint and independent are not the same. Disjoint, we are using that when we're using a single trial or one trial. If they don't occur, they cannot occur at the same time. Independent, we're using multiple trials, and we're talking about one event affecting the probability of the next. Okay. Okay, so here's some examples. We can say, are they disjoint or are they independent, or are they not disjoint? Or are they dependent? Okay. Okay, first example. Choosing a beverage from the fridge, and it's either a diet soda or a water. Okay, so these are going to be disjoint events, because if you're selecting a single beverage, it cannot be both a diet soda and a water at the same time. It has to be one or the other. Okay, Dennis ordered a steak, Lois ordered a salad. Disjoint, independent, not disjoint, not independent. In other words, dependent. So Dennis orders a steak. Are these consecutive events, or are these a single trial? These are consecutive events. Okay, so we're either asking, is it independent or not independent? Well, we don't know if Dennis ordering a steak would make Lois want to order a salad, right? We don't know that for sure. So we can say that these events are independent. They are independent events because the probability of Lois ordering a salad most likely didn't change once Dennis ordered a steak. Lois probably knew she wanted a salad to begin with. Okay. Selecting a card from a deck of cards in the event that it's a queen or that it's a heart. So first of all, are we talking about a single trial or consecutive trials here? Well, again, the key word here is A. A means one, right? So a queen or a heart. Are we talking about disjoint or not disjoint? This is not disjoint, right? Because the queen of hearts can be chosen. Okay. All right, selecting 2 marbles from a bag of 12 blues and 7 reds, and having the outcome be that the first is blue and the second is red. All right, so is this a single trial once again, or are these consecutive trials? Once again, key word, right? We're selecting 2 of them, one after the other. And by the way, this is without replacement. I have to say without replacement because if it's with replacement, then it changes. Okay. In this case, these are not independent. These are going to be dependent because the probability of selecting a blue on the first, so B1, is 12 out of 19 marbles. But the probability of selecting a red, given that we selected a blue, well, there's 7 reds left, but there's 18 left in the bag. So the old probability, or the general probability of selecting a red, is 7 out of 19. So you can see that after we have selected a blue, it changes the probability of selecting a red because there's only 18 marbles left. Okay? So not independent, in other words, dependent. That's the end of the